In this example, let's now investigate the rotational motion of the fluorophore. We will measure the fluorescence anisotropy decay using the appropriate EasyTau wizard. The temperature-controlled sample holder is already loaded with the sample and with a cuvette containing a Ludox solution. Again, we start with an empty workspace and call the appropriate wizard. The sample is coumarin 6 in propylene glycol. Let's choose a username and set the desired temperature. Stirring is not necessary now. A blue laser diode is an appropriate source for a coumarin dye. We select the appropriate detector and grating combination. The wizard is able to locate the emission maximum for you but it is always possible to enter the wavelength directly. At this moment, we are ready for the next step. Similar to the simple lifetime wizard, this optimizer finds the optimal laser repetition rate, temporal binwidth of the TCS/PC electronics, and the appropriate signal count rate in order to record the decay curves as fast as possible. The optimization is now finished. The decay curve fits nicely into the available time window, determined by the highest laser repetition rate applicable for this sample. The detection count rate is adjusted to be roughly 1% of the laser repetition rate and is checked for both vertical and horizontal polarized emissions. We can now move forward and acquire the final decay curves. The wizard runs a quick trial measurement. Based on that, it suggests a 4-second measurement for each emission polarization. Of course, the user can select a different stop condition, for example 15 seconds of total measurement time. It is possible to periodically toggle the polarization during the runtime, but this is useful only for very long measurements. The vertically polarized emission is recorded first. After 7.5 seconds, the emission polarizer is rotated to horizontal and the second decay curve is recorded, again with 7.5 seconds of acquisition time. The histograms are clearly different at the beginning but become almost identical afterwards. This is a clear signature of a slow depolarization. An optional next step is recording an instrument response function. The system automatically moves the scattering solution into the beam path and sets the appropriate measurement conditions. The whole process takes just a few seconds. At this point, the measurement procedure is completed. We can exit the wizard and the result will be saved and transferred to the workspace. Data analysis is just a few clicks away. We now open the experimental results in FluoFit. There are many ways to analyze anisotropy data. The most powerful one involves a global reconvolution analysis of the two polarized decay curves. The simplest possible case is assumed by default. That is, a symmetric spherical freely rotating rotor with a single exponential intensity decay. It is enough to press the start button. We can see on the fit results that the model describes the data very well. The major results are the fundamental anisotropy of 0.38, which is very close to the theoretical limit, and the rotational correlation time of 3.3 nanoseconds. This type of analysis finds the fluorescence lifetime and the G factor as well. There is an alternative, less precise but simpler analysis scenario. We can calculate the time-resolved anisotropy directly from the intensity decay curves according to the definition formula of anisotropy. In this simple case, fitting a single exponential decay curve without any reconvolution recovers practically the same anisotropy parameters: fundamental or initial anisotropy of 0.38 and a rotational correlation time of 3.3 nanoseconds.